Way back in 1994, a hugely important paper came out called A Note on Distributed Computing. And you know what? Its lessons are probably more relevant today than they ever were. It completely dismantles this beautiful but really dangerous dream that still kinda haunts the software we use every single day.
But let's start with something we've all been through. You're using an app, and then, poof, it just freezes. You get that spinning wheel of death, and you're just stuck. You have no idea if it crashed or if it's just thinking really, really hard. So what's actually going on under the hood?
Well, it turns out the root of that super frustrating experience often comes from this really powerful idea from the early days of networked computers, an idea that tried to make a very, very complex world seem deceptively simple.
So what was this big idea? It had this kind of grand name, the vision of unified objects. And let me tell you, it was a truly seductive dream. The promise was to completely erase the line between code running right there on your computer and code running on some server thousands of miles away.
The core idea was this. As a programmer, you shouldn't have to care where your code is talking to. Is it an object in the computer's memory, right next to it? Or is it on a server on a different continent? Who cares? The code you write should look exactly the same. The system was supposed to just hide all the messy details of the network. I mean, just think about how appealing that is. You write your logic one time, and you just let the system figure out the rest. It's the ultimate dream of simplicity. And, as this paper argues, it's fundamentally and, dangerously wrong. All right, so where does this beautiful dream start to fall apart? Well, the first and most obvious crack is something we've all felt, even if we didn't have a name for it. It's just the unavoidable reality of physics. It's latency. And look at the sheer scale of the problem. A local call happening inside your computer takes nanoseconds. A call across a network takes milliseconds. We're talking about a difference of up to 100,000 times. That's like comparing the time it takes you to snap your fingers to the time it takes to fly across the entire country. You just can't pretend that difference doesn't exist.
But here's the thing. As huge of a deal as latency is, the paper argues it's actually a distraction. It's the obvious problem. Yeah, it's the tip of the iceberg. But it masks these far more profound and irreconcilable differences between local and remote computing.
And this gets us right to the heart of the argument, failure. But specifically, a type of failure that literally can't happen when all your code is just running in one place.
Think about it this way. When a program on your own computer fails, it's usually total. The whole thing just crashes. Boom, done. But in a distributed system, one piece, a server over there or a network connection here, can fail while all the other parts just keep on running. This creates this messy, unpredictable state of complete uncertainty. Is the server down, or is my connection just slow? Did my request even get there? Who knows? And this messy, uncertain state has a name: partial failure. And it isn't just some occasional bug. The paper calls it a central reality of distributed computing. The possibility that part of your system is broken at any given moment changes everything about how you have to design software. You can't just wish it away.
Now you might be thinking, okay, things can fail. So can't we just write better code, make it more robust, or maybe buy a better network component with a higher quality of service? And the paper's answer is a big, emphatic no. See, the problem isn't in the implementation. It's baked into the interface itself. The paper gives this perfect little story, the parable of the queue. So imagine your app sends a job to a remote server. The network times out. Did the request make it? You have absolutely no idea. So to be safe, you send it again. But what if the first request did get through, it was just slow coming back? Well, now you just sent the same job twice. A totally reasonable strategy, retrying, has just created chaos.
And you see, no amount of robust implementation on that queue could have solved this. The problem is that the interface, the way the two systems talk, didn't give the app a way to handle the uncertainty of partial failure. Robustness has to be designed into the very language that the different parts of the system use to communicate.
And this isn't just some abstract theory. The paper uses a classic, real-world example of what happens when you ignore these problems: the network file system, or, as you might know it, NFS.
The whole goal of NFS was simple: make files on a remote server look and act exactly like they were on your local hard drive. Same commands, same interface. But by hiding the reality of the network, it backed its users into a corner with an impossible choice. So here's the no-win situation. With soft mounts, if the server suddenly disappears, your app gets an error and moves on. Sounds good, right? Well, not when it tries to save data to a file that isn't really there and silently corrupts everything.
The other option, hard mounts, prevents corruption by freezing your application solid until the server comes back, which could be seconds or hours or never. That is the painful consequence of pretending a remote file is the same as a local.
So what's the big lesson here? What's the takeaway? The paper's conclusion is really a call to action for anyone who builds software. Stop trying to create these elaborate systems that hide the network. Instead, build systems that acknowledge the network and actually design for its unique, and yes, sometimes messy, properties.
And to do that, you basically have to burn these 4 irreconcilable differences into your brain. 1. Latency isn't a bug, it's a fundamental constraint. 2. Memory access is completely different. You can't just pass around pointers because a memory address in one machine is meaningless on another. 3. Partial failure is the norm, not the exception. And 4. Concurrency, with a million things happening at once, is genuinely chaotic and unpredictable.
In the end, the goal isn't to create this perfect illusion that the network doesn't exist. It's to acknowledge the difference and to build robust systems that respect the reality of a distributed world. So the next time you design a system, or even just wonder why your app froze again, ask yourself, is this system respecting the network, or is it just pretending it isn't there?